The first talk is by Dr. Farhan Saif, who is a professor in Qaid-e-Azam University. And I'm really glad to welcome him to this conference to give the invited talk. Just a brief introduction of him, even though he is quite well-known and famous in quantum optics and quantum information community in Pakistan, because of supervising and training a lot of students from Qaid-e-Azam University. He has been a professor in Qaid-e-Azam University for about 1.5 decades, and he has won several awards, especially the Abdul Salam Prize for Physics, Pride of Performance, and the Gold Medal from Pakistan Academy of Sciences. And it's a really great pleasure to have him. Welcome, sir, and please, okay, so you already are able to share the screen. The floor is all yours, sir, and the participants, if there is any question, please post it in the chat, and I would put them to Dr. Farhan Saif at the end. Dr. Saif, can you please check if you're unmute, because I can't hear you.
Well, when I'm there, I want to full screen the right here. Yeah. Okay. So many thanks for inviting me in the conference. I'm delighted to be here. Keeping in mind the Nobel Prize of the year, so I have slightly modified the title of my seminar. So I'm going to talk about the engineering entanglement optomechanically in complex dynamical systems. So I'll be presenting a small layout of my presentation. So I'll start with the historical background, then I'll explain the way optical fields exert forces on matter, and particularly atoms as well. And then we shall see how we can write a hybrid optomechanical system and talk about the effect which is coming from the complex dynamics, is dynamical localization. And let's see how we can develop the entanglement in these kind of systems. So if we talk about the evolution of the subject, so it started with the first observation of Ibn al-Hashim. So he's very much known as Al-Hasan. So he explained the theory of vision. So he explained the concept of vision, and he changed the previous understanding and pointed out that it is the light which is falling on the objects and coming to our eyes, and that make it possible to see. So as an evidence, he said that the small amount of intensity entering into our eyes and high amount of intensity entering into our eyes affect differently. So that was a very simple detector. So later in 1577, Peter Arpian pointed out another interesting thing, that the comet tail is behind the comet. So it is in the opposite direction to the sun. So it was calculated by Lebedev and Nicholas and Hull separately, that this force is directly proportional to intensity. This force can be very small on a particle on Earth. This radiation pressure force can be very small, maybe acting on a particle on Earth, it is something like 10⁻⁻18 Newton, as compared to the gravitational force on the object. So, but still it is sufficient to make the beautiful shapes of nebula, for example. And in recent work, it is possible to make the satellites move in space with the help of this radiation pressure force. Another interesting force which we find when we talk about atoms, so that is the optical force which is exerted on the atoms once the atom perform transitions. So this force is related to the gradient force, and it has been responsible to make the optical tweezers. And then it is also very accurately used to use, this force is also helpful to make traps. really sorry. I'm really sorry. So here we are. So, well, it is, can you see me? Hello, can you see me? Well, we have the connection or?
Yes, sir. We can hear you perfectly fine, and your slides are also okay.
Weird. Excellent. Excellent. So, well, this force, this force which is used to make the optical tweezers.
Okay, we can see your slides again.
So here we are. So it's possible to develop the condensates with the help of the force exerted on the atoms. So now, if we combine the radiation pressure with optical cavities, so this becomes an interesting regime where we can have various different effects, and we can simulate various different quantum mechanical systems. For example, if we have an optical cavity, so in there we can have countable infinite modes. So the modes which are existing in the cavity should fulfill a basic requirement between the length and the wavelength. So the length of the cavity should be integer multiple of half of the wavelengths. So this generates the corresponding frequencies. This provides the corresponding frequencies of the modes which we can have inside the cavity. And from here, we can also calculate the free spectral range, which is the difference of frequencies between two neighboring modes. What happens, very interesting, that if we move the position of one mirror slightly, so this introduces shift in the frequency. So we can see that the previous frequency is slightly shifted because of the small shift in the displacement of the mirror. Now, if we have mirrors so light, if the end mirrors are very light, so that the radiation pressure force can move them, so we shall be seeing a constant variation in the frequency, so of the field, and the field would be surviving there naturally, so far as the requirement of the length and the wavelength is provided. That length of the cavity should be integer multiple of the wavelength. Now, so this is an interesting scenario. Now, what happens that once we apply the light field over the moving mirror, so the mirror is displaced. So as the mirror is displaced, so what we see that the amount of radiation in the cavity changes. So if the change in the position is significant enough so that the condition of length and the wavelength is gone, so then we should be seeing that there is no radiation available in the cavity. So this is a back action of the mirror. Now, the displacement in the mirror position and the variation in the radiation pressure are the cavity effects which are modifying the radiation pressure force in the cavity. So in the presence of radiation pressure force and resultant movement of the mirror acts as a nonlinearity for the electromagnetic field. Now, this simulates the nonlinearity of the medium that a field observed while interacting with a medium. So in this way, we are in a position to develop the experiments which we do with the medium and the field in the optomechanical domain because we are in a position to generate the same nonlinearity. So this opens up a quite interesting domain. But we see that the photon carries an energy and it has a momentum, which we have h bar k. Energy is h bar omega. So if this photon falls on the end mirror, it provides a change in the momentum of the mirror as delta p is 2e by c. If the photon stays in the cavity for a time delta c, so the radiation pressure provided by the field by the cavity field, which may have n number of photons, appears to be n delta p by delta t, and we can write this n e by l. So this leads us to write the corresponding potential, which is provided by the optical field photons on the mirror as minus n e by l, with q as a displacement. Q we write as the delta x. So sorry, there is no qm. I change it with q. So now, this way we are in a position to write the quantum mechanical description of the potential, and this is n is the number of field photons, so we write a dagger a, and q is the displacement operator, so it is q sitting here. In explaining or presenting the system mathematically, we write the corresponding Hamiltonian, and it is comprising the cavity Hamiltonian, it is comprising of mechanical mirror Hamiltonian, then the interaction between the mirror and the field which is making the which is exerting the which is provided by us to develop the cavity field inside. So if we write them, so the cavity field is expressed quantum mechanically as h bar omega c a dagger a plus half. H mirror is taken as a harmonic oscillator kind of performing oscillation, and then we just develop the interaction between the cavity field and the mirror. So this is that part, and this is the driving field or the laser field which we're providing from outside. So this way we are having a mathematical description of our experimental system. This simple optomechanical system can be developed in various different ways, and we can talk about matter field-like interactions, and it is we are in a position to develop the couple this system with nanomechanical membranes, single or multiple multi-level atoms, or BEC and fermions. This all has a work in mind that we can develop. We can make gravitational wave detectors, optical tweezers, optical fluid devices, and many other applications. So this is a very sophisticated regime in which we are in a position to have radiation pressure force providing us nano devices or devices. Fine. So if we want to present these kind of systems, which are in the simplest way, we may consider that is a field which is provided from outside, this laser field. It is entering into the cavity, making the cavity field mode, and this cavity field mode is sufficient enough to make the end mirror move. And due to the movement of the mirror, there is a effect on the radiation field inside that we're discussing. So we may introduce, as we're talking about, that we may couple these systems with cold atoms, with membranes, fermions, and so on. So we pick up BEC and couple our optical cavity field with BEC, and now our end mirror is moving due to the radiation pressure force in the presence of the condensates. Now, mathematically, this is done by adding one more Hamiltonian term, and where we have a Q describing the position of the condensate and P corresponding momentum. So we can write the corresponding Hamiltonian in this way. We can add this into our complete description of the Hamiltonian mathematical system. And zeta SM is basically describing the coupling of the condensate with the optical fields. So we want to talk about the evolution of the system, and that we perform by writing the corresponding quantum Langevin equations. And these quantum Langevin equations are providing us the equation for the displacement of the mirror with P and Q, and they are also describing the displacement equations for the position of the condensate as P and Q, and A is the operator corresponding to the field inside the cavity. So in total, there are 6 equations: 2 for P and Q, 2 for capital P and Q, and 2 for A and A dagger. So we consider there is a field is strong inside the cavity, and this gives us the cavity field description in the form of laser field amplitude. And once we apply this in these equations, we can write the second order differential equation for the displacement operator for the end mirror, and the displacement operator for the condensate. What we see distinctly, that if we don't have second term available to us in both the expressions, so this is describing in classical domain a harmonic oscillator. So in that sense, the second terms in both the equations are corresponding to the nonlinearity, which we're just discussing, due to the coupling with the end mirror movement and the coupling with the condensate and the field. Now we may consider that we may consider regimes to make in order to simplify our discussion. We pick up the regime where we have a small coupling, a very weak coupling between the condensate and the field. So this gives us a possibility to ignore the second term here, and we write the Q, which is the position operator for the position of the condensate in classical domain as harmonic oscillator. And we obtain from here the corresponding potential for the position of the this mirror Q. And once we substitute this in the complete Hamiltonian, so we are writing the Hamiltonian for the system, and again saying the same thing, that if we don't have this, the last term, so this is simply describing the Hamiltonian for a harmonic oscillator. So P squared by 2m plus half m omega m square Q square, and this is the nonlinearity term coming because of the moving mirror and the radiation pressure force. So if we look at the coordinates, Q minus lambda is cosine of 2 omega RT, and we enter into the moving coordinate domain, so we can calculate, we can rewrite the same Hamiltonian in a different form, where we separate the time dependent and the position dependent parts. So in that sense, our first two terms becomes describing the Hamiltonian of the system once we don't have any explicit time dependence in the system. Say if we don't have the movement of the mirror, so then this Hamiltonian is sufficiently expressing the entire system. And in the presence of the movement of the mirror, we find the appearance of this last term. So in total, this system is having 3 dimensions, P, X, and T, and they are coupled. So we can write the corresponding phase space in the classical domain, and we see it is a mixed phase space. We have stability islands, and there are stochastic seas around these islands. So this is a typical description of a classically chaotic system or complex. We see the complex dynamical scenario. We have resonances in the system, and we have complete disordered dynamics around these resonances. So in the quantum mechanical domain, if we compare the classical and quantum mechanical dynamics, so we see the classical system will show a growth in the variance, whereas in the quantum mechanical domain, we find it follows the classical behavior for some time, but then it shows a saturation. So that means the variance is saturated, is showing a saturation beyond a certain time. And this is describing the localization phenomena, or sometimes we say as dynamical localization phenomena. This is happening in position space, and this is happening in the momentum space. So the mirror, the N mirror, is describing or presenting a localization both in position and in momentum domain. We see the corresponding probability distributions, and we see that our quantum mechanical object is visibly localized compared to the corresponding classical object. And if we want to present the same thing on the logarithmic plot, so we see there is a fast decay beyond a certain position, and our mirror is localized in position and momentum space. We can see the same behavior over long time, and we can show that if we were having a classical dynamics only, so it was going to display a dispersion. It is the width of the distribution is growing all the time, as we were seeing in our plots as well. But in the quantum mechanical domain, we see that the width becomes saturated, and it is no more expanding in the as we proceed in time. The same is happening in momentum and position domain. So this was for momentum, and this is for position. So this is also expressing the same thing, that if our mirror was a classical mirror, showing a classical dynamics, so then it was going to show a spread all the time. And if it is a quantum mechanical object, it will show a localization. Okay, so this is quite interesting, because you're talking about the spread of the mirror dynamics. So it is a quantum mechanical object, so we can understand this thing. So we can calculate the variance for various different h-bar values, or Planck's constant values, as a function of the modulation which we are providing to the system. And we see that as we reduce the value of h-bar, the variance start increasing as a function of modulation. So what we should expect, that if h-bar is 0, so this green curve would be approaching to the red curve. So this is the same up here. So this is telling about the extent of the quantum mechanical effect into the system. We can show in the same way the localization of the BEC under the condition of weak mirror field coupling. So, so in that sense, we're in a position to show how our condensate will be localized. And we see this in the distribution of the condensates, and also we see in the evolution of the condensate in space and time, and in momentum space and in time. So this is a confirmation that we have dynamical localization in the system, and the presence of dynamical localization is considered a signature of quantum chaos into the system. So this proves that our system is supporting quantum chaotic dynamics. So we calculate the time in the same way as using the Langevin equations, and we calculate the logarithmic negativity into the system. So that helps us to provide a measurement of the entanglement system. So we are talking about the entanglement of the N mirror and the field, talking about the entanglement of the cavity in the absence of any BEC. It was place. So if we calculate the entanglement between the end mirror and the cavity field due to the radiation pressure force, so we see the entanglement takes place as a function of the coupling and as a function of detuning. So when the detuning is 0, so we see the maximum. When we have resonant scenario, delta is equal to omega m, so we have the maximum entanglement and then it drops down. And then we can also calculate the entanglement as a function of the temperature for 2 different values of the coupling. So if the coupling is large, so we see larger entanglement. And if the coupling is small between the field and the end mirror, so we find a small entanglement in the system. We can add the condensate into the system and see that our condensate is also playing a role in controlling the entanglement. So we calculate the logarithmic negativity again, and so this gives us an entanglement between the atom and the field, and here we have the entanglement between the mirror and the field, and in the last we have the mirror and the atoms. So this gives us an understanding that we can develop the entanglement between the systems. Now, as a function of temperature, we calculate and see that the mirror cavity entanglement is there for 2 different values of the coupling. And so we find the entanglement between atom and the mirror and the cavity in the absence of the condensate, when the atoms are not coupled to the cavity field. So then we have a larger entanglement, but now once we have the field present, atom field coupling is available, we have a smaller amount of entanglement and so on. And the interesting thing is that we also have the entanglement between the mirror and the atoms, but this is quite fragile because it stays for a very small temperature. It is in microkelvin. System scale is in Kelvin domain. So so here I submit my thanks, and I wait for any questions.
Thank you very much, sir, for the excellent talk. There are a few questions, and there are a couple of them related to the equation on slide 32. So the first question is that, can you please explain more how the strong field limit allows you to solve the 6 differential equations?
Well, you see, we have these Langevin equations, quantum Langevin equations. So we have equation for first order differential equation for P, and then for Q. If we take the second derivative, so you would see that in the on the right hand side we get Q dot, and if we substitute this quantity here, the Q dot equation here, so we get is let's do the other way around. If we take the second derivative up here, so we have a P dot equation here, and we can substitute all this expression, and this will give us this equation, which we are writing as d2q by dt square, and this is harmonic oscillator within nonlinearity, nonlinear harmonic oscillator equation. And the in similar way, we can write the equation up here for the position of this position operator for the our condensate. Now, we want to apply the small coupling regime. Say we want to have small coupling between the atom and the field. So that will mean that theta Sm is small, and we can ignore this term. So then this gives us an understanding that our condensate is almost behaving as if it is a harmonic oscillator. And we put this up here, and this gives us an expression of this form. So we are working under this small coupling regime. Small coupling between the condensate and the field.
Okay,
Similarly,
so in the same vein, the next question is, how do you think we can access the strong coupling regime using this setup?
well, if it's a comparison, it's a comparative statement. So what we say, theta Sm is small, so understanding that zeta would be very large. So it is
Right.
just so that's a strong coupling regime in that sense. It's strong coupling in the sense of field and the end mirror coupling. So that coupling is strong compared to zeta Sm. So
Okay. Please go ahead.
I explained that we are coupling the zeta Sm with zeta, and then we say it's a weak coupling compared to the other coupling. So the other coupling is strong in that sense.
Okay, so there are a couple of other questions. Let me group them all together because they're related to adding terms to the Hamiltonian in the master equation. So 3 people have asked how were you able to add the phenomenological terms in the master equations, and in the same vein, how was the effect of the temperature and a mirror, which is a macro object, was taken into account?
Well, you see, it's. I think you're talking about this Hamiltonian.
Yeah.
So it's so what we have the field, we have the mirror, and then we have the coupling between the mirror and the cavity field. So we write the field Hamiltonian, and then we write the mirror Hamiltonian, and then we write the corresponding interaction between the two. And this is the input field which we are providing. So this way we are in a position to have a general Hamiltonian for this system, and that we are doing on the next slides.
Okay, so let me just ask you the final question. There are actually a few more questions, but we are getting out of time. So if you can kindly go through chat and respond there later. But
I would very much, any question you can write me directly. Or,
okay.
Anybody interested?
Yeah.
Go ahead.
So the last question is, does this interaction entail mirror behavior or an actual interaction of quantum plus classical object interaction? I mean, is the mirror only an effectual term here?
Well, you see, we are taking the mirror as a quantum mechanical object. So, so there is a understanding. We have entanglement, and entanglement is a between mirror and the field. So we are taking the mirror itself as a quantum mechanical object. Then we are explaining, then we are showing the mirror to be dynamically localized. And the appearance of dynamical localization is a quantum mechanical effect. So that is that is why it is understood as the appearance of quantum chaos or quantum complex dynamics into the system, if we have dynamical localization. So our mirror is a quantum mechanical object.
Okay, thank you very much. So maybe the last one, not the final question, because this thing is coming to my mind, that when you did the numerical simulations, I see that there is a term which is m referring to the mass of the mirror. So what was the value for that taken into account? Because that could, perhaps answer some of the questions that people had about the mirror, because it seems to be a macro object which is taken as a quantum mechanical oscillator.
Fair enough. Well, this is quite an interesting thing, because this mirror is a very delicate mirror to the. I mean, it can feel, it can experience, and it respond to the radiation pressure force. So the weight of the mirror is in nanogram. So this is very, so in that sense, it enters into the discussion of nano devices.
Okay. Thank you very much, sir, for the very excellent and interactive presentation. So as Dr. Franz have said, so if somebody has any other questions, they are free to write to him by email. Okay, so thank you very much.